Howdy, howdy. This is Mr. Potter, and welcome to day 2 of our section 3.3 lecture. You may remember in our last lecture we talked about the power rule, the idea that if I have x raised to some nth power and I want to take its derivative, I end up with n times x to the nth minus 1 power. So what we're going to do today is we're going to talk about some related rules using the definition of the derivative that we've been working with our difference quotient. And we're going to come up with more rules to deal with different functional situations. The first function situation that I want to deal with is this function that I've got here. I've got y equals x squared times the quantity x cubed plus 1. And if I want to figure out what the derivative is, it seems like it should be obvious that if the derivative of a sum is the sum of the derivatives, and the derivative of a difference is the difference of the derivatives, that the derivative of the product should be the product of the derivatives. The problem is if I take the derivative of each term and I say that y prime is equal to the derivative of the first term times the derivative of the second term, which we will just say right now that's bad. If I do that, taking the derivative of x squared gives me 2x, and taking the derivative of x cubed plus 1 gives me 3x squared. And so this derivative comes out to be 6x to the third. The problem is that if I use algebra and actually take this and distribute it, where y is actually equal to x to the 5th plus x squared, and then try and take the derivative using the rules that we talked about yesterday, the derivative of x to the 5th is 5x to the 4th, and the derivative of x squared is 2x. And these are clearly not the same function. So then the question is, if I get two different answers, which of these answers, if either, are the correct one? What I want to do is I want to take a look at the product of two functions, f of x times g of x, and I'm going to let y be equal to this product. So if I want to find the derivative of this, I'm going to have to find the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x, all divided by h, just using the standard definition of derivative. My function evaluated at x plus h minus my function evaluated at x, all divided by h. And I'm going to rewrite this, but I'm going to add a little bit of space here, and I'll show you why in just a second. So it's the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x all divided by h. And what I'm going to do is I'm going to add a couple of terms in here. I'm going to add f of x plus h times g of x. And then I'm immediately going to subtract it. So what I'm doing here is I'm really making sure that I add 0 here. I haven't changed the value of my derivative. What I'm going to do instead is I'm going to group it separately, because addition, the order or the way that we associate doesn't really matter. So I'm going to take a look at these first two terms and write this as a limit. The limit as h approaches 0, f of x plus h times g of x plus h minus f of x plus h times g of x all over h. And then I'm going to add these terms. The limit as h approaches 0 of f of x plus h times g of x minus f of x g of x all divided by h. And I want to treat this algebraically because I'm looking for something that I recognize. And the first thing that I see is that this f of x plus h and this f of x plus h are a common term. I could factor out f of x plus h. And if I do that, I'm left with g of x plus h minus g of x over h, the limit as h goes to 0. And if I look at the second term over here, I'm going to notice that I've got g of x for both of these terms. So I could factor a g of x out and be left with f of x plus h minus f of x all over h, the limit as h approaches 0. And I'm starting to notice some things coming together. First this term here looks suspiciously like a derivative of the function g. So what I've got is the limit as h approaches 0 of f of x plus h times the limit as h approaches 0 of g of x plus h minus g of x all over h. And over here I'm noticing that this term looks suspiciously like the derivative of the function f. So I've got the limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x all divided by h. And I know that this actually is the derivative of g. Over here, as h goes to 0, this is just a function of f. So this ends up just being f of x. And over here, this limit ends up being just the limit of g of x. But this term here ends up being the derivative of f. So what I've got is I've got f of x times the derivative of g plus g of x times the derivative of f. And that's what the derivative of a product is, using the product rule. So the derivative of f times g is going to be equal to the first times the derivative of the second function plus the second times the derivative of the first function. So what this means is if I go back to my previous example, this x squared times x cubed plus 1, the rule says that it should be the first function times the derivative of the second function plus the second function times the derivative of the first function. So I'm going to have x squared times the derivative of x cubed plus 1 plus x cubed plus 1 times the derivative of x squared. And now if I calculate this, I'm going to have x squared times, this ends up being 3x squared plus, this is going to be x cubed plus 1 times 2x. So this is 3x to the fourth plus 2x to the fourth plus 2x, or 5x to the fourth plus 2x. Notice that I've got agreement with what I got when I took the derivative of the distributed polynomial. And I don't get what I thought should make sense by taking the derivative of the first function times the derivative of the second function. I have to use the product rule. The product rule says I'm going to take the first times the derivative of the second plus the second function times the derivative of the first function. Now, we were expecting what we knew from limits, the idea that the limit of a product is equal to the product of the limits. And what we've discovered is that for the product rule, that's not so. So what we need to do now is talk about the situation where we have a quotient of two functions. So let's say that y equals f of x over g of x. And so what I need to do is see what happens to this derivative again from a limit standpoint, so that I can come up with some type of formulaic approach whenever I have a rational function. So if I want to find the derivative, that's going to be the limit as h approaches 0. My function evaluated at x plus h, so it's going to be f of x plus h over g of x plus h minus my function evaluated at plane x, f of x over g of x. And this is all going to be divided by h. Now this is ugly. I'm dealing with fractions within fractions. And so I'm going to deal with this in a two-step process. The first thing is I'm going to get a common denominator here. And the second thing is I'm going to rewrite this dividing by h as multiplying by 1 over h. And so this ends up being the limit as h approaches 0 of my common denominator. This has a g of x plus h term. It's missing a g of x term. So I should have f of x plus h times g of x. And this has the g of x term. It's missing the g of x plus h term. So it's going to be f of x times g of x plus h. And in the denominator, I'm going to have both factors of my common denominator, g of x and g of x plus h. But I'm also going to have the 1 over h that contributes the h to the denominator. So I'm rewriting this in a simpler fractional format, not this compound fraction that we had over here. And as we did before, I'm going to rewrite this limit with a bit of a gap in it, because I'm going to add a clever form of 0. So I've got f of x plus h times g of x. And then over here, I'm going to have minus f of x times g of x plus h. And this is all over my large common denominator, g of x plus h times h. And what I'm going to do is I'm going to add a clever form of 1. I'm going to add something in here. I'm going to first subtract f of x times g of x. But I can't willy-nilly just subtract stuff, so I have to compensate by adding it back again, f of x times g of x. And as I did before, I'm going to rewrite this as two separate limits. One limit involving these first two terms. So I'm going to have the limit as h approaches 0 of f of x plus h g of x minus f of x g of x over my common denominator g of x plus h times h. And because I've taken these two terms, all I have left is this term and this term. The problem is that whenever I'm looking at the form of a derivative, the x plus h term should come first. And I'm looking at this, and the x plus h term isn't really coming first. So I'm going to rewrite this as a subtraction of the limit as h approaches 0 of this term minus this term, basically multiplying through by a negative 1 in order to get the first term, the positive term, to be my x plus h term. So I'm going to have f of x times g of x plus h minus f of x g of x all over this common denominator of g of x plus h times h. And as we did before, I'm going to take a factor out of the numerator. So in this case, my factor in the numerator for this first limit is g of x. So when I factor it out, I get g of x times f of x plus h minus f of x. And this is all over a common denominator of g of x times g of x plus h times h, the limit as h approaches 0. Minus, over here my common term is the f of x, and so that's what I'm going to factor out. The limit as h goes to 0 of f of x times g of x plus h minus g of x, all over my common factor, g of x plus h times h. And I know you have an incredible urge to eliminate this common factor of g of x, because that's what we've done with derivatives, is eliminate a common factor in the numerator and denominator. But remember that the common factor we were always trying to eliminate was h. This isn't h. I need to eliminate this h. I need to do something with this h. And the something is to bundle it together with this function. So what I've got is the limit as h approaches 0. This is really g of x times the limit as h approaches 0, f of x plus h minus f of x all over h. And all of this is being divided by the limit as h approaches 0 of g of x times g of x plus h. I'm making it that the limit of a fraction ends up being the limit of the numerator divided by the limit of the denominator, and the limit of a product is the limit of the first term times the limit of the second term. And I'm going to do the same thing over here. The limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x plus h minus g of x all over h. And all this is being divided by the limit as h approaches 0 of g of x times g of x plus h. And several things happen here. One is this limit here is the derivative of f. Two, this limit here is the derivative of g. And three, when I take the limit of this denominator, it's just g of x times g of x, or g of x squared. So my denominator ends up being g of x squared, and my numerator ends up being g of x times the derivative of f. minus f of x times the derivative of g. And this is all over g of x quantity squared. So what we have is that if I have a function f of x over g of x, and I want to take the derivative, it's going to be equal to the denominator's function times the derivative of the numerator's function minus the numerator's function times the denominator's derivative function over the denominator function squared. So this quotient rule, this bottom times derivative of the top, or minus the top times derivative of the bottom over the bottom squared. This is how I deal with rational functions. So let's take a look at an example of a rational function. Let's say that I have y equals x squared minus 1 over x squared plus 1. So that means that the derivative has got to be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. And so this ends up being x squared plus 1 times 2x minus x squared minus 1 times 2x, all divided by x squared plus 1 squared. And this answer is good enough for the AP exam. If I take it another couple of steps, if I actually distribute in the numerator, I'm going to have 2x cubed plus 2x minus 2x cubed plus 2x all over x squared plus 1 squared, which gives me 4x over x squared plus 1 squared. And this is equally correct. This just takes a little bit more algebra, but this is going to be something that's much easier to substitute values in. If I want to find out, say, when my instantaneous rate of change is positive or negative or 0. So this is an example of how we use the quotient rule. I want to do another example of the quotient rule. Let's say I've got the function 1 over x cubed. So if I have the function function 1 over x cubed, and I want to take its derivative, that should give me the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. But we already know that the derivative of a constant is 0. So this term goes away. And over here, I've got 1 times something. So this ends up being the opposite of 3x squared over x cubed times x cubed is x to the 6th. And so I've got negative 3 over x to the 4th, but I really want to write this as negative 3 times x to the negative 4th power. Because we notice that the derivative of x to the negative 3 power is negative 3 times x to the negative 4 power. And this looks suspiciously like the product rule, where we had x to the n equals n times x to the n minus 1, because negative 3 minus 1 gives us this 4. Now, the example that we proved yesterday only dealt with positive integral exponents. So the question is, can we extend this to negative exponents using the quotient rule? So here's our more generalized power rule. Let's say that I want to take the derivative of x to the negative n. That really means that I'm taking the derivative of 1 over x to the n power. And according to our quotient rule, it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over my denominator squared. And when I simplify, the derivative of a constant is 0, so this term goes away. I'm going to end up with negative n times x to the n minus 1, because that's just the derivative of x to the n, over x to the 2n. But remember that when I'm dividing by an algebraic expression, that really means I'm multiplying times its reciprocal, which in this case would be x to the negative 2n. And when I multiply terms, I add the variable exponent. So I have negative n times x to the n minus 1 minus 2n power. But this is really negative n times x to the negative n minus 1. And so the derivative of x to the n is still n times x to the n minus 1. I still have the negative n as the new coefficient, and the negative n minus 1 in my exponent. So this power rule that we talked about, that we thought only worked for positive exponents, positive integral exponents, now in fact works for both positive and negative exponents. The last thing we're going to talk about is we're going to talk about higher ordered derivatives, because one of the things that we've noticed is that f prime is a function. And so it'd be quite easy to just go ahead and say, I want to know what is the derivative function of my derivative function. And Isaac Newton dealt with this quite a bit. He called this, f second derivative, or f double prime. So this is our second derivative. And Leibniz did this as well. He said he wanted to take the derivative of the derivative function, and his notation ended up squaring the d in the numerator and squaring the differential dx in the denominator. So this is the dx, d squared y over dx squared. Of course, for laziness purposes, we do tend to write this as d squared y over dx squared. And so we can take a third derivative if we wanted to, and the notation there would be d cubed y over dx cubed. We could take the fourth derivative, but we're not going to write I here. We're just going to put a 4 in parentheses to indicate that we're taking the fourth derivative. But we'll still use the d4y over dx to the 4. And I can take fifth derivatives, sixth derivatives, and so forth. So for our last example, I'm going to let y be 5x cubed minus 3x to the fifth. So the derivative using the power rule, the power rule here would give me 3x squared times 5 gives me 15x squared, and 5x to the fourth times 3 gives me 15x to the fourth. My second derivative would be 30 x minus 60 x cubed. My third derivative would be just plain 30, because the derivative of a constant times x would just be a constant, minus 180 x squared. And if I continue to take derivatives, I get y fourth derivative would be derivative of a constant is 0, so I end up with negative 360 x. I could continue taking the fifth derivative, and that would just give me negative 360. And because that's the constant, the sixth derivative would be 0, as would the seventh derivative, as would the eighth derivative, as would the ninth derivative, and so forth. So what we've talked about today is we've talked about how to deal with more complicated functions, products of functions, quotients of functions, and we've also come up with a more generalized form of our power rule. So once again, this is Mr. Potter. Thank you for watching. Have a great day.